Hi, everyone. Welcome and good evening. My name is Benjamin Quinn, and on behalf of Harvard Bookstore, the Harvard University Division of Science, and the Harvard Library, I am excited to introduce this virtual event with Dr. Peter Fisher discussing his book, What is Dark Matter, in conversation with Dr. Melissa Franklin. Thank you for joining us virtually. Today's event is the latest installment in our Harvard Science Book Talk series, which works to bring the authors of recently published science literature to our Cambridge community and beyond. On Thursday, November 10th, Dr. Peter Pesek, director of the Science Institute at St. John's College, Santa Fe, will join us virtually for a discussion of his latest book, Sounding Bodies, Music and the Making of Biomedical Science. This evening's discussion will conclude with some time for your questions. If you have a question for our author at any time during the talk tonight, click on the Q&A button at the bottom of the screen and we'll get through as many as time allows. And finally, in the chat, I will be posting a link to purchase What is Dark Matter on harvard.com. Thank you to our partners at Harvard University, and thank you all for showing up, supporting us, and tuning in support of authors, publishers, indie bookselling, and especially for science. Now, without further ado, it is my pleasure to introduce tonight's speakers. Peter Fisher is the Thomas A. Frank Professor of Physics and currently serves as head of the Office of Research, Computing, and Data at MIT. He has served as a referee for several journals, as well as editor for the International Journal of Physics and Modern Physics Letters. He carried out one of the first dark matter searches, and since then has searched for dark matter on Earth and in space, including inventing a new kind of detector, the dark matter time projection chamber. Tonight, he is joined in conversation by Professor Melissa Franklin, the Mallinckrodt Professor of Physics and Director of Graduate Studies at Harvard University, where she is presently searching for new physics beyond the Standard Model. Tonight, Peter and Melissa have joined us for a discussion of what is dark matter. Peter's latest report on the current state of the dark matter problem, which Juan Koller of the University of Chicago calls accessible to any curious reader. It will benefit those that desire to go a bit more technically in depth into the subject matter. Filled with anecdotes, this cohesive and fluid book is a great invitation to learn more. We have a lot to cover this evening, so without further ado, I am delighted to turn things over to our speakers. The digital podium is all yours, Peter.
Hello. Hello, Melissa. How are you?
Hi. So good to be here. I enjoyed reading your book and it was very fun and I learned a lot. Yeah.
Thank you. There were moments it was fun to write, but it was also a lot of work.
I hear only 10 years.
It was 10 years, yeah. Not continuously. I did some things in between. So I was just going to show some slides to kind of set the scene, and then we can talk about things a little bit.
Sounds perfect.
Okay, so here's the bottom line up front, which is the title of the book is What is Dark Matter? This was the title Princeton University Press assigned to me. They have a series of books, What is Blank? So I just slotted into that. But the answer is that we don't know. We don't know really whether dark matter is a particle, or a heavy particle. It could be a light particle. It could be little tiny black holes from the beginning of the universe, or it could be something we haven't even thought of. So kind of that said, the questions I'd like to try to say something about is, how do we know there is dark matter? And why is dark matter so hard to find? And I'll just say that dark matter first made its appearance arguably in 1985. And so that was almost 40 years ago. And despite 35 efforts on the part of me and many other people, dark matter has not been observed in a way that we can say what it actually is. And so I'd like to try to communicate why that is so difficult. We've been diligent. We're not lazy. We haven't been wasting time, but we haven't succeeded. So I'll put some slides up. These are pictures, and I have 7. I always like to say how many slides because people want to know if there's 7 or 77. So just give me a second here. Hang on, there's a little noise in my house. Hey guys, a little more quiet, please. My wife and daughter are having an animated conversation while they are making dinner. They could be attending my talk, but they're okay. So okay, so Melissa, are you seeing the slides okay?
Yep, I see them. It looks great.
Okay, so what is dark matter? This first slide encapsulates 100 years of very difficult scientific work with an unexpected outcome. So in the last 100 years, a little bit more than 100 years, astronomers and particle physicists worked kind of side by side, but parallel play, not together. And so let me summarize the last 100 years of particle physics. Quantum mechanics was invented in the 1930s, and then the theory was developed so that we understood how atoms and some things about nuclei worked in the 30s and 40s. And then 1950s, with this wonderful tool called quantum field theory, there was just this explosion of understanding. The post-war era brought accelerators and new kinds of particle detectors, and lots of particles were discovered, and a lot of theoretical work was done. And then in the 70s and 80s, a real consistent picture of three different kinds of interactions between particles: the electromagnetic interaction, the weak interaction, the strong interaction emerged, and they were put together in one framework, which is called the Standard Model. And in the 1990s, when I became active in the field, we were testing the Standard Model and finding the last few particles, and that concluded in 2012 with the discovery of the Higgs boson. So now we have a theory with 17 particles. We know all of the interactions between them. The interaction strengths have been measured. All the particles' properties have been measured pretty well. There's still some work to do. And in the late 1990s, we thought this was just great, that we had figured out everything about everything. That wasn't true. So going back into the 1920s, that was the era of the first large telescopes, and this part's about astronomy. And astronomers used these telescopes and began wondering whether these fuzzy stars that they observed were balls of gas inside of our Milky Way galaxy. That was one school of thought. Or whether there were other galaxies outside of the Milky Way that were very, very far away, millions of light years away. And in the mid-1920s, Hubble, one of astronomers that the telescope is named after, showed that in fact these nebulae were actually different galaxies that were millions of light years away from Earth. And then shortly thereafter found that they were all moving away from the Earth, which meant that the universe was expanding, which is actually something that Einstein's theory predicted. And then through subsequent years, astronomers, they did a lot of things. They're very busy people. They studied the way galaxies moved with respect to each other and the way stars moved within galaxies. And the only way they could come up with explaining how everything was moving in the biggest scales of the universe was the introduction of matter that we couldn't see. And there were actually two kinds of matter that we couldn't see. One got the name dark energy, and that makes the universe as a whole expand more quickly than we expected based on Einstein's original theory. And the other was dark matter. And dark matter makes particles or stars within galaxies move more quickly than you'd expect from the mass in those galaxies. And they arrived at the end of the 1990s with this pie chart. People like me had been, and Melissa played a big part in all of this. We had been studying the little section of the pie chart, which is 4%, which is called stuff we know about. And that's atoms and molecules and DNA and water and air and cats and everything. And then the other 96% were these new substances. And I always find this an interesting thing to talk to people about, because is this success or failure? We thought we knew everything as particle physicists, and some were very arrogant about it, including me. And then astronomers come along and say, nah, you don't know 96% of what's going on. So the dark matter is what I'm interested in, and I can say more about dark energy and maybe why I'm not so interested in it if somebody wants to ask a question. But we're going to talk about dark matter, because dark matter could be a particle that we don't know about, or it could be little black holes, or it could be some particle that's been predicted by one of the many theories that have come about. So let me just tell you a little bit more about how dark matter works. Let's see. I've somehow lost my cursor. Hang on a second. Okay, this is a picture of the galaxy Andromeda. It's the closest galaxy to the Milky Way, and it is about 2 million light years away. And it looks very similar to the Milky Way. And in the middle, you can see this glowing region. In the very middle of that, there's a big black hole, about 1 million times the mass of our sun. And there's a lot of matter being pulled in to the dense central region. And then you can see there's kind of this beautiful pancake shape with spiral arms that looks kind of cloudy. It's not really cloudy, those are all stars. And there are about 1 trillion stars in this picture. What's particularly interesting is you can see that there's kind of a sharp end to the disk part, or the pancake part that I mentioned. And that shape and that edge is really only explainable if you hypothesize that there is some substance called dark matter that is making a gravitational field that makes that shape. You can't make that shape using just the gravity from the stars. It really requires that there be this large diffused sphere of dark matter surrounding the galaxy and extending actually many, many times the radius out to the side. We can use telescopes, astronomers can use telescopes to measure how fast these stars move. And in fact, the stars all orbit the bright central region, and they go around once every 200 million years. And measuring the velocity, it turns out that the stars are moving a lot more quickly than one would expect from the gravitational force of just the stars. So this is really saying that there is some substance in this huge structure, and I'll tell you this is about 50,000 light years across, that is not seen. And not seen means it's not creating light, because the only way we can detect something in a distant galaxy is by the light that's created. So instead of this really being the scientist's picture of a galaxy, the theoretical picture of a galaxy really is like this, where in the middle, You can see the disk where there are dark matter, and baryons is the fancy name for all the stuff we know about. You can see I've marked that our solar system in the Milky Way is about halfway out of this disk. And then around it is a spherical halo of dark matter. That there's about 10 times as much dark matter as the rest of the matter in the galaxy. And it's making the right kind of gravitational field for the galaxy to have this really quite remarkable, beautiful disk shape with the spiral arms. So this is actually a really remarkable picture. This is a picture of many, 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 many galaxies. And this was a picture that was taken by the Hubble Space Telescope. And it's called the Extremely Deep Field. And what they did with Hubble was really quite remarkable. This is a telescope that's in orbit, so it can take very high resolution, very precise pictures. And one of the major projects that they carried on over the 2 decades, or 3 decades now that it's been in orbit, is to take a picture with a very, very long exposure of the darkest part of the sky. So this is a picture of the Fornax constellation. And everything you see in this picture, almost, except for 1 or 2 objects, is a galaxy. And you can see they have all kinds of different shapes and colors, and some are big and some are small, and some of them are just barely 1 pixel on your screen, barely visible. And that's a galaxy of 1 trillion stars on the other side of the universe. So this is to give you some idea of just the plethora of different shapes and sizes. And a careful study of all these different kinds of galaxies always comes up with the same conclusion, which is that the stars are moving too fast to be explainable by the amount of light coming from that galaxy. And this must denote the presence of dark matter around all galaxies. And this is, there have been very detailed measurements of literally thousands of galaxies, and they all show these features. So dark matter is really something that's pervasive. Now, you might think, well, what's the big deal? Maybe dark matter is just a kind of another kind of particle, and there are lots of particles, so what are you worried about? Well, actually, these are all the particles that we know about. In the green are quarks, and these are particles that make up nuclei. In the purple are the electron and its cousins, and below the electron are the neutrinos, which are the other cousins of the electron. The cyan down the right side are all the different particles that make forces and hold things together or cause things to decay. And then off to the very right there is the Higgs boson, which is the particle whose interaction makes mass for all these other particles. It makes them heavy. And I'll just mention that my interlocutor, Melissa Franklin, played a really important role in discovering 2 of these, the top quark and the Higgs boson, and maybe one I don't know about. But the thing about this is there are these 17 particles, and there's a theory, which is a set of rules. And I'll tell you, you could write down the rules. The rules for the standard model, how all of these things are interact are about as complicated as the rules for bridge. You know, it's not simple, but it's not real hard. And if you wanted to, most people can figure it out. The other thing, though, that's quite remarkable and important is that this theory is complete. And there's no room for anything else in this theory. We could add something to the theory, but that would be an enormous change, and it would mean that new particles would have to be discovered or new interactions would have to be discovered. But as this stands, these 17 particles and the rules that tell us how they talk to each other doesn't have room for anything that could be dark matter. And that's just where we are. So let me show you one more picture. This is a picture of the sky that's kind of been unrolled into an oval. So looking straight up is the center of the oval, and looking straight down is kind of the whole edge of the oval. And this is a map of the temperature of the night sky with all of the stars and all the galaxies subtracted out. And that leaves just the light from the Big Bang. And the Big Bang happened 13.8 billion years ago. And when the Big Bang happened, about 400,000 years later, at the formation of neutral hydrogen, light was released, and the light had slightly different temperatures depending on where it came from. And in 1963, this light was first observed. It's called the cosmic microwave background. And since then, it's been carefully mapped. So this is a map of the temperature of the sky. And the average temperature is about 3 degrees Celsius above absolute zero. But it's not the same other places. And the reason it's not the same at all places is that some places there was a little bit more dark matter, and some places there was a little bit less. And on this map, the places where it's red, there was a little bit more, and the places where it was blue, there was a little bit less. And these variations were caused by quantum mechanics. Quantum mechanics has uncertainty. So if you have some matter uniformly filling the universe, the density isn't the same every place. It's different and it changes just quantum mechanically. And so by looking at this, we can figure out the size of galaxies and something about how they formed just from the quantum mechanics of dark matter. And again, this is an astronomy picture, and the picture is consistent with there being about 23% of the matter energy in our universe being dark matter, compared to 4% of the stuff we know about. So those are really 3 examples of why we know there's dark matter. There are many, many others. Most of them come from astronomy, or they all come from astronomy. And it's pretty much inarguable that there is something in the universe that's filling the universe beyond the stuff that we've been studying here on Earth. So that's how we know there is dark matter. I'll just tell you, I'm going to stop sharing, if I may. Is that okay, Melissa?
Yep.
Okay.
Great.
Okay, and I'll just tell you why it's hard to find. And I have a little audiovisual aid for this. This is a little box that I made. And there's one theory of dark matter, which I sort of like and I studied for a long time, but I got tired of it. But it's called the WIMP theory, weakly interacting massive particle. If that theory is correct, there is one dark matter particle in this box. And the reason it's hard to find dark matter is, okay, there's a particle in this box, but there's a billion protons in this box. And there's 3 billion electrons in this box. And there's a couple of muons, and there are a whole bunch of other things in this box. So here on Earth, it's hard to find dark matter because there's so much normal matter around that when Melissa and I do experiments, all we're doing is sorting particles. And inevitably you make mistakes. And if you make a mistake 1% of the time, that means if you sort 100 particles, one of them you're going to get wrong. To find dark matter on Earth, you have to sort a billion particles and not make a mistake. And that's really difficult. The size of a galaxy, though, there's 10 times more dark matter than there is normal matter. So that's why it's an astronomy problem. You have to look and think about galaxies as a whole. in order to find dark matter.
So,
Anyway,
when you say there's one dark matter in that box at any one time,
yeah.
is it moving through?
Oh yeah, it comes and goes, you know. And if it's primordial black hole, it's much less frequent. But yeah, but on average, there's one WIMP, 100 GeV WIMP is in this box right now, and also, you know, a few in your head. Think about that.
Yeah, I think about that all the time. Great. So you actually are making it clear how hard the problem is, and people have been working incredibly hard, and you talk about all this in your book. I just want to talk briefly about this series of books called Princeton Frontiers in Physics, which this is part of. There's some other books like How Do You Find an Exoplanet, or Can the Laws of Physics Be Unified? And it's kind of an interesting series because it's perfect for somebody. It's good for many people, but it's perfect for somebody who's had some physics education and then wants to know what's happening in the field at any one time. And I think I learned a lot from it, and I'm not just a person who knows a little bit of physics, but I think an undergraduate after taking quantum mechanics, it would be perfect for. And then even for somebody who doesn't have any physics, there's something you can get out of it. I like the way you started when you said if you have ghosts in your house moving things around, you can't see them or hear them or anything, or feel them. But the objects in your house get moved around in weird ways. And so all you want to do is figure out from the movements of the things what exactly is going on. And this was your analogy for dark matter affecting how the matter we see moves around. I thought that was very nice. But I'm hoping the ghosts are not scary.
Well, it's creepy. I mean, it's creepy in our universe, isn't it? That there's all this stuff there, and it's always been there, and it took us like 5,000 years to realize it. That's you know, what else are we missing?
What else are we missing? Yeah.
I don't, yeah.
So I guess one of the really interesting things, and you mentioned this already, is that you go through the early universe in this book, and you sort of say what happened, and you say, you know, we have this great standard model, but the standard model is only 3 of the 4 forces that exist. We don't have a standard model for gravity. We don't have a quantum theory of gravity, and yet in the very beginning of the universe, you say it's got to be quantum mechanical. I mean, it's very tiny and high energy, and we don't have any theory, and that there's all these things that might have happened that we can only tell from the light we see now, the cosmic microwave background that you talked about. So can you talk about that a little bit? Because you write something really nice. You say the cosmic microwave background carries the imprint of quantum mechanical variations in the density of dark matter at the time of hydrogen formation. So that's after the universe has inflated. And I just wondered if you could tell a little bit about that story.
Well, yeah, I mean, well, I'll just put a plug in for a much better book than mine called The First 3 Minutes by Steven Weinberg, who explains this in great detail. The thing I find remarkable about the picture that I showed is that you're really with undergraduate quantum mechanics, you learn enough so that you can see that picture has to be quantum mechanical. It has to be the product of some quantum mechanical system, by which I mean quantum mechanics. You're really seeing quantum mechanics when you're seeing the fluctuations, the things changing. And you people, you know, if you want to think about a fluctuation, go if you have a top loading washing machine, you know, start it and open the lid, and then put your finger on the little button to hold it down so that your washing machine is running, and you'll see the spindle going back and forth, and you see the water sloshing around. And every once in a while, you'll see water kind of come bloop, and there will be like a drop that hangs there for an instant and then falls back in. That's like a quantum mechanical fluctuation. It's something that appears and then disappears in some very random process. So at this time, before the light from the Big Bang, and this time, this very, very early, before much matter had formed, this dark matter is just roiling around, and every once in a while there's kind of this bloop of a much denser region, and then it disappears, and the imprint is just a snapshot. It's of one of those instances where you can see a few of the little blips and not others. It's a little bit, I was trying to, an analogy that I didn't use making the book is, it's like, suppose you took a picture of the surface of a swimming pool 5 minutes after some number of children had gotten out of the pool. So you'd still see some rippling around, and could you figure out how many kids had been in the pool?
Or maybe they were ghosts.
Or maybe they were ghosts. Yeah.
So I was also interested, I'm interested in everything. You talk about this idea that I haven't really thought about before, which is that just after the universe, it just started, inflation happened. We don't know if inflation actually happens, but let's imagine inflation happens. Then just after, you say there's possibility that there's some very heavy mass primordial particles.
Yeah.
I have no idea what they are, that then decay. And, it makes you think, really? Like, what were they? I want to know what those are. And
so do
those
I.
aren't in the regular, those aren't in Weinberg's first 3 minutes, I think.
No, he was a very circumspect man. I'll just say anything, but he was very careful.
Yeah. So tell me, are those just something that you like to think about, or are they something you think might be real?
Well, I mean, you've worked at colliders like I have, and you know that there's this kind of hierarchy. You have this big accelerator, it knocks two protons together, and the two protons make something very heavy, like two top quarks, which weigh about 200 times a proton. And then the top quark decays to a lighter quark, and then the lighter quark decays to an even lighter quark, and then that decays to some photons. And there's just this cascade down to the lightest particles that are around. And one just naturally imagines that in the early universe, we see the first part of that cascade, which is although it's kind of going backwards, it's a formation, and you kind of, we kind of see the protons forming, and then deuterons, heavier and heavier particles are getting built up. And where did all of this come from? It's natural to think it came from the decay of something, but maybe it was a soup of really light particles that all got pushed together and made heavier particles. I don't know.
Yeah, I don't know either, but it was an interesting idea. Yeah, I made me think that maybe there was something to look forward to when we were able to get the collider up to an energy. Maybe
Yeah,
maybe
well,
I'll be a ghost by then, but yeah. So the other thing that I found really interesting, you talk a lot about how this scientist Zwicky in the 20s or 30s first saw a little bit of evidence for dark matter, but the instruments he had to actually measure things weren't so precise. And so it wasn't until sort of 1970 when Vera Rubin and Kent Ford realized that they could go back to this problem with better instruments. And I thought that was really interesting, because that happens a lot in science.
Yeah.
And but still, it takes some kind of, it's like a little bit of brilliance to realize what you can go back and do at a time. Because so, you say that, dark matter, the idea of dark matter really became prominent in the 80s, and that was after they had used better equipment that they made, right, to map out the dark matter in all of these different galaxies. Is that sort of the story that you would tell?
Yeah, well, I mean, so all of this, is driven by technological advance. Zwicky made his observations on Mount Wilson in a little observatory next to the 100-inch Mount Wilson telescope. And so on the Mount Wilson telescope, all the other astronomers, Walter Baade and all those guys, they're clawing each other's eyes out to look through the big telescope. He just went to town on this little Schmidt telescope that was only 18 inches, but it had a very wide field of view, so he could get this whole system of galaxies in one frame, and so that he could measure their velocities and their positions very accurately. And that's where his original observations of dark matter came from. He wrote this incredible paper, which I'm sure you know all about exactly this topic. He was an awful man, by the way. Nobody liked him because he was very mean to people. I tell my students about this because it just doesn't pay.
It doesn't pay
to be mean to people unnecessarily. Hang on,
no, but
I'm going to get a power cord. I'll be right back.
Okay.
My computer's telling me it's about to run out of batteries, and it's making me really nervous. Probably can go.
So in this book, so there's so many things I want to ask you actually, but in this book you go through all the possible candidates that could be dark matter, and you say that. So first of all, you say, how do we know there's dark matter? And you go through all the evidence for that. And then you say, okay, how are we going to figure out what it is? How are we going to figure out who these ghosts are and what they're doing? And you go through like primordial black holes. And, the first thing I think you talk about is, failed stars. And I realized immediately I didn't know what a failed star was. So I had to look in the glossary, which is very good in this book.
Yep.
And to find out what that was. And then there was possibility that it's some kind of beyond the standard model particle that we would have to add to the standard model. And there was the fact that maybe gravity is different than we think it is.
Yeah.
And I guess they're really, really interesting. It's really interesting to read everything about the new detectors and all. It's pretty up to date. So you must have just finished it recently.
July, yeah.
It could be axions, which are other particles that we don't know whether they exist or not. So it's kind of exciting. And I thought that you say at one point, you say, for this one detector to measure axions, the amount of power that this experiment is able to detect is about the same as that entering your eye from a 100-watt bulb 20 million kilometers away.
Yeah.
And that's kind of like, it's so exciting. So in all of this story, what you get from this book is that a lot of people have been doing a lot of experiments in very smart ways with very good detectors and to figure this out. And we haven't figured it out yet, but it's incredibly exciting. I just wondered whether you're feeling that.
Well, that's what drew me to it. The big experiments at accelerators are they're really exciting because the level of technology is so high, but it's all known technology because by the time you build one of those things, you have to be sure that it's going to work. And the dark matter was, experimentally, it's kind of the Wild West. You have all the, and lots of dark matter people, they're all like kind of wacko. and they do really extreme things. I mean, we did experiments way far underground to be away from cosmic rays. We built an experiment that's sitting on the space station now, which was, you know, absolutely hell to do. And there are all these really kind of extreme detectors, like, you know, being able to measure 10 to the minus 24 watts of power, which is, you know, phenomenal that those experiments are able to do that. And you're just driven to think about these things because really it's this sorting problem. It's this 1 in a billion million. You know, you have to have something really weird and different and new to be able to get at that.
So okay, I have 2 more questions before we're going to questions from the audience. And I have exactly 0 minutes, so I'll ask them very fast, okay?
Okay.
One is, I want to know what you think is the most likely candidate. That's just, but the other thing I'm a little worried about is, can you talk about, imagine that dark matter doesn't have any other interactions other than gravity. So
Yeah.
you just have gravity. So a lot of these experiments are not going to work.
Yeah.
And is that a possibility? So first of all,
Absolutely.
you know,
Absolutely.
absolutely. Okay, can you tell us a little bit about that?
Well, I mean, it could be exactly what you say, that none of my experiments worked in the sense they didn't find dark matter. They set limits and they got students PhDs and things like that. But I mean, one of the, and I know you know this, one of the hard things about science is there's no guarantee of success. I mean, you set your sights on something and you know, maybe you discover something or maybe not. I think one of the key things about it is really just the journey or the quest. And I've been fortunate that I've worked with mostly people I really liked and respected, trying to do these really hard things. And you know, we've kind of moved each other forward in our lives, and that's, you know, that's really why we do this. And you're director of graduate education, so you obviously know, and I know you know, the great joy in teaching a graduate student something and learning from them. Yeah, because one of the things most people don't realize is the professors learn as much as the students do. You know, because students come with, you know, they say all kinds of things, and if you're paying attention, you think about some of them and you really learn something. The first question, you know, what if I could choose what dark matter was, I'd choose primordial black holes. I really like primordial black holes. And these are black holes.
Sorry, in the book you say it's almost impossible to see them.
Yeah. I'm thinking, I spend a lot of time thinking about how to find them. And you know, there have been some great experiments, you know, by people from Harvard even, looking for versions of primordial black holes. And I think it's a place I want to go to next. I like it because, you know, you don't need any more theory to explain them, because you've already have gravity, and presumably gravity knows how to do that. And you don't need to add anything to the standard model. So that's all set. We don't have to mess with that, because, you know, any change to the standard model is just going to be a mess. It's going to be really inconvenient. We'll have to learn things again.
Okay, primordial black holes, which are just black holes that are made in the early universe and very small. So could you say how big they are?
Yeah, so black holes have this special place, special radius called the event horizon. And once you cross the event horizon, you can't come back out. So the lightest a black hole that would still be in the universe can be is about the mass of a comet. And the event horizon on a black hole from the beginning of the universe with about the mass of a comet would be a little bit less than the radius of a proton. So, tiny. And they could just go straight through Earth. They don't pick up much matter. They can go straight through pretty much anything and nobody really notices. They're really pretty cool. And, it's just such a simple thing. And, Stephen Hawking is famous because of this paper about black hole evaporation. That paper was written to explain why there weren't more primordial black holes in the universe. So if you look at the 1972 Hawking radiation paper, which he's famous for, because that's the one place where we see quantum mechanics and gravity coexist, there's two references in that paper. One is to Joe Weber, and the other is to a previous paper he wrote calculating the density of primordial black holes, and it was much too high. And so we had to figure out some way of getting rid of them.
Interesting.
So I think they're really cool. They're really simple. You don't have to learn a bunch of new theory or anything. They're just pretty hard to find, but
pretty hard to find. Okay, so that's what you're going to be working on in the next 10 years.
Yeah.
Okay.
You want to help?
Yeah. No, I think I'll come. Yeah. So,
Okay.
Benjamin Quinn, I think it's time for us to have questions from the audience. I hope I haven't asked all the questions.
You certainly haven't, Melissa. There are quite a few in the queue, so let me work my way through them. Okay, so Peter, when you started by saying that you weren't going to talk about dark energy, people immediately wrote with some questions. So I'm going to ask one that I think summarizes all of them. So Carlos Castro asks, how do we know that what we... Oh, so sorry, reading the wrong question. Stephen Katona, sorry, Stephen, says, since matter and energy are intimately related, can you speculate on possible relations between dark matter and dark energy?
Yeah, I mean, they're pretty different. So the thing about Einstein's theory of gravity is there's this one equation, and the one equation relates the way this universe bends and expands to the matter content, the matter and energy content of the universe. So if you know the matter and energy content, you can tell how the universe is going to change. All dark energy is the addition of one number to that equation. And it explains everything we observe about dark energy. So that's why I first of all, I'm not terribly interested. We've measured, or not me, but astronomers have measured that one number. They now know it to a few percent, and that's dark energy. Dark matter is really explainable by a new kind of particle with all the messiness that particles bring. So there isn't a simple relationship. I think many of us believe that there's kind of a theory of everything, or some unified theory, and they would be related in that theory, but we don't know what that theory is. So we have gravity and we have everything else, and sort of dark energy is over here in the gravity part, and everything else is over here in the everything else part. I mean, dark matter is over the everything else part.
Great, thank you. So now I will ask some questions about dark matter and its speculation. So Bill Blumberg asks, thanks for a superb talk. Can you comment on the theories that the effects of what we call dark matter is actually the consequence of not understanding gravity on very large physical scales?
Yeah, so that was one of the most interesting things about the book, was that was an area that I hadn't really followed, and I did a lot of reading about it, and after a while I kind of began to believe in it. I showed two pictures from two different telescopes. One was Andromeda, and you can see the effects of dark matter there, and Andromeda, kind of the characteristic size of Andromeda is, let's say, 50,000 light years. dark matter explains the same features in the picture of the light from the Big Bang, and the size of that picture is kind of 14 billion light years. And so it's, one reason I chose those two is the very different scales, 50,000 light years and 14 billion light years, are explainable by the same particle phenomenon. And I don't think anyone's found a way to really do that by just modifying gravitational field. You can choose, I mean, and what people have done is they've been able to explain the way Andromeda looks by changing gravity. It's a perfectly reasonable thing to do. But then when you look at, well, what's the constant consequence of the light from the Big Bang, it doesn't work out.
Wonderful. I'm going to move on to this next question, which is sort of about technology, and I'm interested to sort of hear about your experience with the technology used for this. So interesting kind of analogy. So Cameron Clayton asks, UFOs are often just the result of the device used to view them. Is it possible how we make the measurements might cause us to overestimate the role of dark matter? And so I guess just a question about technology.
Yeah, no, that's, yeah, you know, every observing system brings what we call, and you know, just on UFOs, in the early part of the Cold War, the United States built a line of radar stations along the Arctic Circle called the Distant Early Warning Line, and these were big radars, and they were looking over the North Pole, where we were expecting if the Soviet Union ever attacked, there'd be planes coming over the, and so there were 20 or so of these stations running 24/7 with operators just staring at these displays. They
Oh,
Ooh,
oh,
so
no,
abrupt.
what
Oh
happened?
gosh.
Oh, I guess, I
Uh,
bet he can plug in his power cord.
Oh gosh. Okay.
So, well, no, well, I'm sure he's going to come back. What do you think? I think he will come
I think
back.
he will as well. I think he will figure out the question. So let's.
In the meantime, I can just say that there's a couple of other things in this book that are really nice in case you haven't decided to buy it yet. But one of the nice things he talks about is if dark matter annihilates somewhere up in the sky, about the magnetic fields that are outside the atmosphere. The magnetic fields, you know, there's an Earth magnetic field and magnetic fields out. Ah, there he is, outside the
There he
atmosphere.
is.
I was filling in for you and telling them your story about beautiful magnetic fields outside our atmosphere, and how the dark matter annihilations were going to send electrons and positrons along those. But I was just filling in because you didn't plug in your power, right?
Well, no, there are other problems, but yeah,
Oh
Okay.
I'm
goodness.
here. I'm
Okay.
here now. I'm sorry.
And you're
Anyway,
back.
so these radar operators saw all kinds of stuff that it took years to explain. And you know, this is where a lot of the original UFO lore came from. So it's always interesting anytime you build you know, a new device, you see things you don't expect, and until you know what they are, they're unidentified. So to answer the question specifically, that is a great question, and if you look in optical telescopes enough, you can see all kinds of weird artifacts that are just features of the optics of the observing system. The key thing is that all of the measurements are made repeatedly using very different kinds of telescopes. So the measurements, for example, I talked about how fast the stars move in the galaxy Andromeda. Those were made with large optical telescopes and also with radio telescopes, you know, very, very different. And it's not a guarantee, but it gives one confidence that the same overall effect is observed in two very different things, one that's looking at light and the other that's looking at radio waves, and they're on different parts of the earth and they operate in very different ways. So it's really repeated observations using several different kinds of technologies. But that's a great question, and it's always something to press scientists on, because people do get stuck on what they do, and there's always the danger of believing it too much.
But sorry, Peter, in your book, you discuss many different ways that we know dark matter is there, from gravitational lensing to also looking at the rotation, how fast the stars move. So it's not just one.
Yeah, it's one phenomenon viewed many different ways, and then many different phenomena viewed optically. People have been busy. I thought when I first started writing the book, I thought this would really be about particle physics, but it turned out it's mostly about astronomy, and I'm not an astronomer.
So I'm going to ask one more technical question, and then we're going to end with a discussion of literature, because we've gotten a few book questions. But I want to ask this question from Sasha von Meyer, who asks, can you talk about the scale of the homogeneity of the background radiation? It seems so much larger than what you'd think of in quantum mechanics.
Oh, can you put that picture back, because you didn't point out the micro Kelvin?
Yeah,
I think that might have been.
I think this is going to be. I'm on my.
Oh, okay. Yeah. Anyhow, the scale, right, was microkelvin. So
yeah, so the average temperature is, and hello to Sasha, who's from out at Berkeley and an expert on the electrical grid. The microwave sky average temperature is about 3 degrees, 2.7 degrees, and the variations are on hundreds of microkelvin. So less than 1,000th of a degree Kelvin. And you can put in the conditions of the emission of the microwave background and then propagate backwards in time. And you get a temperature that kind of makes sense, although it's a pretty big extrapolation for variations on that scale.
So I'm going to sort of, I guess, return to the question of primordial black holes, because we got a few questions about them, lots of interest. And I guess I'll just ask the simple. So how are you going to find them, or what exactly is the sort of venture to finding them, or where does it begin?
Well, so I didn't invent this. And I mean, let me back up a little bit. I guess in the mid 80s, the idea that dark matter could be, stars that didn't quite make it and collapsed into something dark, a failed star, came up. And as a general class of object, these were called massive compact halo objects, or machos. And so these were any objects that contained significant matter, let's say the mass of a comet or heavier. And these could just be floating around the galaxy and we wouldn't see them. And so there was a couple of really impressive experiments using a phenomenon that Melissa mentioned, where if you could look at a bunch of stars that were outside of the galaxy, and one of these things came and moved in front, they would cause the star to appear brighter, because the gravity of the star actually acts as a lens. And so that is kind of the classical way of looking for a primordial black hole, which is what I'm interested in. It's difficult because the experiments that were done in the 80s and 90s and in the early 2000s we're looking for heavier objects where the lensing effect was larger and of longer duration. So they could just look at all these stars, 5 million stars every night, and you kind of expect the brightness variation to take place over days. As they get lighter, the brightness variation takes place over hours, and then for the very lightest, minutes. And there have been a couple of interesting measurements done using the trillion stars of Andromeda to look for this effect. So to me, that's the best bet. Although I've been talking to people who study exoplanets, and they can make very precise measurements of the velocity of a star because of the perturbing orbit of a planet orbiting around this star called an exoplanet. And I've been working on, is there a way that you could look for a star that suddenly just kind of goes like that because a primordial black hole scoots by? So far, no luck. Black holes are tough.
I love the word scoot used in relation to them. So I'm going to ask one sort of final question, which is kind of about the book itself. I'm interested to sort of see where this book might kind of fall on the sort of general audience members. So Lewis Friedman asks, would your book be good for someone who has never studied physics except maybe eons ago in high school? And also asks or someone else asked rather, like how did you kind of start with dark matter? Or what was the first thing you read? It's a two-part question, I guess.
Oh, what was the first thing I read? Yeah, I had a pretty rough introduction to dark matter, actually. For my PhD, I did an experiment looking for a very rare kind of decay. And I had built this detector more or less by myself. Well, I mean, no, that's not fair, but I had been kind of in charge of it. And we had it in this freeway tunnel that went through the Swiss Alps because this was very susceptible to cosmic rays. And so we used an Alp to stop cosmic rays. So this was a very, from a radiation standpoint, quiet environment. So I was happily doing this experiment. And I had been at it for a few years. And I was living in Switzerland. My PhD advisor was Felix Bohm. He was at Caltech. So I was unsupervised, which was great. We went to a conference in France one January, and I was actually writing my thesis, and a guy named David Spergel, who was an astrophysicist from Princeton, gave a talk basically saying that dark matter could be these WIMP particles, weakly interacting massive particles, and if they were, they would bounce off nuclei and leave a very tiny amount of energy that could be measured. And he said the kind of experiment that could already do this was exactly what I was doing. And so my advisor turned to me and said, oh, you have this great opportunity to do some wonderful science. I mean, I was writing my thesis, I really wanted to get that done. But I listened to him. So we made some simple modifications to that experiment, and did one of the very first searches for particle dark matter and wrote a paper about it. So the the first paper I read was the one I was writing. But but my introduction was David Spergel's papers. There was another guy later on, Mark Kamiakowski, who along with a few other people wrote sort of the first big paper on dark matter. What was the second question?
Oh, it was sort of just another kind of, is your book a good introduction to this subject? Introduction.
Well, I made a rule for myself when I started the book, which was that I wasn't going to cut any corners and I wasn't going to dumb anything down. And then the third rule was I wasn't going to use any equations. So there's some multiplication and addition, but there aren't any equations. And my hope would be that, and I also tried to explain kind of the core ideas about Newtonian gravity, because that's really the backdrop for this whole story. And so there's about 5 pages that are pretty qualitative about how Newtonian gravity works. And the other thing I kind of realized is that when you write a popular book, you're not trying to teach people how to calculate or how to be, professionals in the field. It's more about art appreciation and explaining something so that somebody understands it, so they feel good about understanding something, rather than trying to explain everything. So I don't try to explain everything. I don't list every experiment, which some people are already unhappy about. That, oh, you didn't mention my experiment. Well, there are like 6 dozen experiments.
Great. So that is I think that's all the time we have for questions.
Can I say one more thing?
Please do.
So if you would like some swag, so if we were in the bookstore, I'd have brought one of these for everyone, and we'd put it together and we'd all look at it. But if you send me a picture of yourself holding my book, having bought it, I'll send you a box of dark matter.
Wait.
Okay.
Can I get one?
Melissa.
Melissa's the first one. That's incredible. What's a good way to reach you, Peter? I'm just kidding.
fisherp@mit.edu.
Awesome.
I will also mention that you can go to OpenSea.io and you can buy the network fungible token for this box.
With dark matter. Awesome. Incredible. Great. So well, thank you both so much. Just any closing thoughts before we end for the evening?
No,
Well,
I
I think everybody should go to Harvard bookstore and buy lots and lots of books, and then come up here to Porter Square Books and get some books there, because independent bookstores are magical. And I mean, there aren't any chains left, really, are there? I mean, Amazon killed everybody, but those are special places, and help them.
Awesome.
Great. Thanks so much for coming, Peter.
Well, thank you, Melissa. This is you set this up, and we got to get together, huh?
Yeah.
Okay. Oh, your student Elizabeth is coming by tomorrow.
Okay.
Great. Well, and thanks to all of you out there for spending part of your evening with us. Please learn more about this book and purchase What is Dark Matter on harvard.com. On behalf of Harvard Bookstore, the Harvard Division of Science, and the Harvard Library, all here in Cambridge, Massachusetts. Enjoy the rest of your evening. Keep reading and be well. Have a good night, everyone.
Bye.
Bye.